All right, today we started our discussion of channel flow focusing on steady uniform flow. And in the case of steady uniform flow, the energy equation reduces to a statement that the channel slope and the frictional losses have to be in balance. To see that, if we consider point 1 to point 2 being along the surface here, then the change in elevation between the two is given by the slope times distance. The energy equation becomes let me write this as y1 plus v1 squared over 2g plus the channel slope times distance is equal to y2 plus v2 squared over 2g plus the frictional losses, or the head loss. Now, if it's uniform, then the depths are the same at y1 and y2, and the velocities are the same at point 1 and 2. So this becomes channel length, or channel slope times length is equal to the head loss. We're going to define the head loss to be something called the friction slope times length. So this becomes the statement that the channel slope is equal to the friction slope. From an energetics perspective, this means that the flow is gathering energy by moving downhill at the same rate that it's losing energy to friction. Now, this condition leads us to a series of expressions that relate velocity and slope and other parameters. The most commonly used one is the Manning equation. I want to emphasize that one here in the review, where Manning's equation says that Q is equal to 1 over n times the area times something called the hydraulic radius to the 2/3, channel slope to the 1/2. The hydraulic radius is equal to the in a wide channel, wide rectangular channel, it's approximately equal to the depth, approximately equal to y. And the area is equal to the width times the y. So what we end up with is that Q is equal to 1 on n times the width, y to the 5/3, channel slope to the 1/2. This result, Manning's equation, is the theoretical balance that would occur if flow was infinitely uniform along our channel. And so we're going to use this to define the third thing I want to put into this review, y sub n, the normal depth. And that's the depth that would occur at this point of balance, so we can invert that, and we can write yn is equal to Manning's n times now little q, which is the flow per width, divided by the square root of the channel slope, all to the 3/5 power. The normal depth is the depth that would occur in an infinitely long uniform channel, or another way to think of it is it's the depth at which the energy is in balance and it's gaining energy at the same rate that it's losing energy. So we have three key results then from lecture today. One relates to the energetics, one relates flow rate to depth and channel slope for uniform flow, and then using that result we can say something about the depth that would occur if we had uniform flow.